In this video, we're going to learn how to solve applied problems using the law of cosines. So in my first example, a motorized sailboat leaves Naples, Florida, bound for Key West, 150 miles away. So I'm going to put that distance between Naples and Key West is 150 miles. Now, maintaining a constant speed of 15 miles per hour, but encountering heavy crosswinds and strong currents, the crew finds that after 4 hours, the sailboat is off course by 20 degrees. So initially they left, they're supposed to go this way, but now they're off course by 20 degrees. So this angle here is 20 degrees, and now they're off in this spot somewhere, which after 4 hours going 15 miles per hour, 15 times 4 is 60 miles they've gone off in that direction. So now, how far is the sailboat from Key West now? So in order to figure that out, I'm going to solve this triangle for the missing side, because I want to figure out what this distance is. So using the law of cosines, which is c squared is equal to a squared plus b squared minus 2ab cosine of c. My c is going to be x for that distance. Is going to be equal to my two sides, which will be 60 squared plus 150 squared minus 2 times squared, not degrees, minus 2 times 60 times 150 times the cosine of 20 degrees, which is where the angle across from x is. So plugging all this in, I'm going to simplify this a little bit. 60 degrees gives me 3,600 plus 15 squared should be 22,500 minus 2 times 60 times 150, which would be 300 times 60, so 18,000 cosine of 120 degrees. Let me just double check that last one. So 2 times 60 times 150, yes, 18,000. And 150 squared is that much. Now I can add together my 3,600 plus 22,500 to give me 26,100 minus 18,000 times cosine of 20 degrees, which gives me x squared is equal to 26,100 minus 18,000, not 1,800, cosine of 20 degrees, giving me 9,185.53. And to find the distance, I just need to take the square root of that number. So the square root of that gives me x is equal to 95.84 miles for part A. So that's how far they are from Key West now. So through what angle should the sailboat turn in order to get back on track? So what I'm looking for is this particular angle here. What is that angle? So in order to find that, I need to find another angle within this triangle, which I can do using the law of cosines as well. So again, if I wanted to find, let's say for example, that angle that I'm missing, I know all three side lengths. So if I wanted to find this angle, which I'll just call angle C for simplicity, cosine of C is equal to c squared minus a squared minus b squared all over negative 2ab. So cosine of C, after plugging all of that in, so c squared would be opposite of the angle first, so 150 squared minus a squared, which I'll say is 60, minus 95.84 squared, all over negative 2 times 60 times 95.84. If I'd say that these other two sides were a and b. So let's plug all that in and figure out what that is. So 150 squared minus 60 squared minus 95.84 squared, all divided by negative 2 times 60 times 95.84. Oop. So I make sure I type all of that in correctly. And now I get cosine of c is equal to negative 0.845. So c is equal to the cosine inverse of negative 8.45. So take the cosine inverse of that value, and that gives me the angle of 147.64 degrees for c. But now I'm not looking for c, I'm looking for theta, but the reason why I found c is that it's a linear pair. So theta must equal 180 minus 147.64 degrees. So the angle that they need to turn their ship would be 32.36 degrees, I guess, to the left of which they're heading. That's for part B. And now I want to find how much time has been added to the trip because of this. So normally they'd be traveling 150 miles, but now it looks like they're traveling 60. So this is for part C. $60 plus 95.84 miles, which would be 155.84. So they're traveling an extra 5.84 miles. So how long is that going to take them if they maintain the same speed of 15 miles per hour? So extra 5.84 miles. And again, that time it would take would be the distance they're traveling over the speed they're traveling, which would be 5.84 miles over the 15 miles per hour. So 5.84 divided by 15 give me that time added is 0.389 hours, or multiply that by 60, roughly 23.36 minutes. So you can see here all the calculations that take place whenever they're fixing. You maybe have to fix like a navigational error to put everyone back on track. And with how much time it's going to take them to get back on course, making that calculation in this time could have saved them a lot of time instead of like just guessing and maybe having to recorrect over and over again. Now let's look at one more example. We have a radio tower, which usually is pointing vertically up, 500 feet high. So this side here is 500. Is located on the side of a hill. So it's vertically up, so it's kind of fighting against. There's a little bit of an angle here. It's not a right angle against the hill to make sure it's vertical of 5 degrees. Is the inclination to the horizontal, which I drew with this dashed line. How long should the two guy wires be? I have here in red. If they are to connect to the top of the tower and be secured at 2 points 100 feet directly uphill, so this is 100, and 100 feet directly downhill. So that's what I know. This is 500, and those two distances are 100, and we want to know how long these guy wires need to be. So the key here is I have two side lengths on these two triangles I've kind of formed on either side of the tower, but I need to know an angle within it, and I'm going to use that 5 degrees to help me out. So I'm going to call this angle over here angle A, and this angle on the other side angle B. And I'm going to redraw the situation taking place right there off to the side. So you can see a better picture of what I'm about to do. A little more enhanced. So again, this is 5 degrees. And if I draw a parallel line to the horizontal, which the tower would also be parallel to, perpendicular to, I can say, since these are parallel, that this angle here would be 5 degrees and that angle would be 5 degrees. Which meaning if this was 90, what's left up top would be 85 degrees. And what's left on the other side would be 90 plus 5, so 95 degrees. I wanted that in purple. So now I know what angle A and B are. A should be 95 degrees, and B should be 85 degrees. Now we're going to find what length these wires need to be to make this happen. Again, this is kind of tricky to try to do some eye work on if you had to do this with like a real life like working problem. So it's good that we make these calculations beforehand. So again, first we're going to find this length. We'll call it A for the left guy wire and B for the right guy wire. I wanted to use purple for A. And I'm going to find, now that I know what angle A is, I'm going to find what this length needs to be using the law of cosines. So I'm looking for A squared, and I know I guess what the other two side lengths are. So B squared and C squared are, and cosine of A. So A squared would equal 100 squared plus 500 squared minus 2 times 100 times 500 times the cosine of 95 degrees. So A squared would be equal to, I'm going to type all that in, so 100 squared plus 500 squared minus 2 times 100 times 500 times the cosine of 95 degrees. And just to double check that I'm in the correct mode, I am in degree mode, so I'm doing all right. 95 degrees gives me 268,715.5743. Take that square roots, and I'll learn that the length of the A side will be 518.38 feet. Now we're going to find the length of the other guy wire, which should probably be shorter since it's more uphill, so it has to travel less of a distance. Should probably be less than 518. But for B, I'll have B squared is equal to A squared plus C squared minus 2AC cosine of B, where B is 85 degrees and A and C are 100 and 500. So now I have B squared is equal to 100 squared plus 500 squared minus 2 times 100 times 500 times cosine of 85 degrees. So again, I'm going to plug back in that same statement from above, 100 squared plus 500 squared minus 2 times 100 times 500 times the cosine of 85 this time. And now B squared equals 251,284.42857. Taking the square roots of that gives me 501.28 feet for the other guy wire, approximately. So yeah, so that little calculation ahead of time made sure whenever I would construct that wire, it's going to be the right length for this tower and not too long or too short. And that is how you solve applied problems using the law of cosines.